Okay, the last thing we did is actually fairly straightforward. We consider two capacitors in series. Now, as we discussed in class, if we start moving negative charges from here to here, and I think I had it going the wrong way when I did it in class. I don't know what made me do that, except I don't even naturally go clockwise. So I don't know what I was thinking. I just wasn't thinking. Okay, but anyhow, negative charges will go from here to here. Conventional charge will go from here to here, so it's like positive charges going around this way. In any case, you move a little charge from here to here. Now, what happens to these two plates here? Well, if we have negative charges here, that's going to repel the positive charges it's going to repel negative charges from this plate. Positive charges in this plate are going to attract negative charges to this plate, and these two plates are going to end up with equal and opposite charges that are equal to the charge that you have on the outer plates, so that you have equal charges on both capacitors. Now, you got some voltage. What is that voltage? Well, if you know the charge Q and the two capacitances, the capacitance of each plate, you can find the two voltages. And by just using the definition of capacitance, you can turn it around to find that voltage is equal to charge over capacitance, so that voltage 1 is charge over capacitance 1, voltage 2 is charge over capacitance 2. Again, this all follows directly from the observation that you're going to have equal charges here and here. And let me make sure we understand, whatever charge goes off of here goes on to here. That's why these have to be equally charged. And we can also argue that these will then have, these plates will have opposite charges to the plates they're opposite from. And of course that gives you net charge of 0 in between here, which has to be, since this is a connected conductor that didn't have any charge to start with. Charges can't jump the gap in the capacitor. Of course they do, they leak, or if you put too much charge on, you get lightning bolts, maybe little lightning bolts, but you get a discharge through the capacitor, kind of ruins the capacitor. But if you have a working capacitor that doesn't leak very much, what we say has to be true. These charges have to be equal and opposite, have to equal to these charges. And they do in any case, even if you're leaking charge. But we're going to concentrate on the ideal case where no charge leaks. Okay. In any case, we get the two capacitances, or the two voltages. Okay. And the two voltages add up to the total voltage, which is then Q over C1 plus Q over C2. Now, what's the capacitance of the system then? The capacitance is charge over voltage. That's going to be Q over V. Well, Q is Q, and V is Q over C1 plus Q over C2. So Q over V is Q divided by Q over C1 plus Q over C2. The Q's will divide out. You end up with the reciprocal of 1 over C1 plus 1 over C2. Now we could put that over common denominator C1, C2, and we could get the expression here. It would be C1 times C2 over C1 plus C2. And you can do that. It's a kind of a handy thing to do. But we're going to instead say, well, okay, the total capacitance is the reciprocal of this. So the reciprocal of the total capacitance is this denominator, so that 1 over your total capacitance is 1 over C1 plus 1 over C2. And that's the rule for capacitors in series. Now, if you have capacitors in parallel, then each capacitor sees the entire voltage of your source, so that you have just a wire here, which is an equal potential, not an equal potential surge, an equal potential volume actually, and same here. And over here you have the same thing. So the voltage across each of these capacitors is V. It follows then that the charge on this capacitor is Q1 equals C1V, and the charge on this capacitor is Q2 equals C2V. Therefore, you have total charge C1V plus C2V with voltage V. So your total capacitance is total charge over voltage, which is C1V plus C2V divided by V. V's divide out, and your total capacitance is C1 plus C2. So when you have capacitors in parallel, the total capacitance is the sum of the two capacitances. Okay, now let me just give you a little preview. When we do resistances, the roles are reversed. And it's going to turn out that if resistances are in parallel, 1 over the total or equivalent resistance is the sum of the reciprocals of the two resistances. And in series, you're just going to add the resistances. Now, you've kind of experienced that in lab already, and of course we're going to be coming up with circuit electricity pretty soon. Okay, so anyhow, here's the law, and here's the way the laws are derived. The derivation for parallel and series resistances is analogous to this, but you end up with kind of opposite results.